What's coming off around here?
If you guys playing railroad anymore today, there's a landslide, a new cut.
I'd like to lead off this episode by expressing my appreciation to everyone who decided to subscribe to Fun with HO Scale Stuff to share my curiously, sometimes divergent HO scale projects. I'm curious about many things, and some of them diverge pretty much from the usual scale modeling videos on YouTube. To tie back to the modeling aspect of our hobby, I want to quickly show this kit I bought. The service yard for the Lehigh Valley Terminal Railroad is going to be a small service facility. So I'm going to use this backhoe model to load coal into tenders and to clean out the ash pit. I have a clam bucket on order as well that I plan to, I'm going to substitute the kit's shovel with the clam bucket. The clam bucket is ideal for grabbing loads straight down. I also want to say thank you for your patience with my infrequent postings. I hope that what I learned from the stuff is being explained clearly and offers you, the viewers, insights into these technologies that are becoming pretty commonplace on model railroading today. Whatever the outcome of my projects, I hope that some of my antics continue to prove to be of interest. Thanks again for sharing my adventures with me. In this video, I'll first provide an update discussion regarding the high let-go hose shields that I purchased, and then I'll present a discussion on the USB hose shield library that I am going to use to create a preliminary Arduino USB driver for the NCE USB interface circuit board. Stay tuned if you like more HO scale stuff. All right, so the last time in the previous video, I was saying that because this hose shield, this was the one that I used originally, because this hose shield had stopped working, that I would just, and then it started working again, so that I decided I'd just continue using it as long as it would work. And okay, folks, it stopped working again. So I have no idea why it's on and off again. So, and I have no way to find out. I honestly have no clue why any electronic device would be intermittent unless it had, in my experience, a physical defect that could possibly be intermittent, like a wire barely touching or something. So I just decided that I'd use this backup one. And then as I was using the backup, or tried to use the backup hose shield, I started comparing them, and there's a whole lot of differences here. And so this was the original. And recall that when I examined this one, I found that there's actually one of the input pins was not soldered, which could be the intermittent problem I'm having, who knows. But there's no, by the way, there's no way to solder that. I couldn't possibly get a solder iron in there. That would have to have been surface mounted, soldered with solder paste. But on the second one, the backup unit, you can't even tell. It's got a shield across there that makes it impossible to see. So there's that. And then the next thing I noticed was that on this one, I remember explaining that the resistors placed in series with this Maxim chip are the wrong values that they should be, and it's even printed on the board. They should have been 3.3 ohm resistors, and they weren't. They're actually 2.2 ohm. However, on this one, they actually got them right. There's 3.3 ohm resistors in series there, so that's a positive. But we'll get into more about this one in a second. But the next thing I noticed was that this one came with little solder balls on the jumpers, like so that 5 volts is being transmitted back out through the host connector, USB Type A, and that the Arduino's supplies, the source pins, are also jumpered here and here. But on this one, you can see the jumpers are unsoldered, and there's no 5 volts going back out. So when I tried to use this one, the library immediately flagged it as an error, saying that the oscillator didn't start. So that was because there was no power. I mean, no, the oscillator won't start if there's no power. So I'm going to have to solder these myself, which actually, because everything's so tiny, I'm not really looking forward to that, because my dexterity is below par, kind of like these units. And so the other thing I noticed is the headers that they provide on the board. These headers are provided so that if you want to plug another unit on top, you can fit it on there. Don't know why you'd want to, because the headers, you know, they're just abbreviated headers. But even at that, I noticed that they're out of alignment on both sides. Both of these are out of alignment. Actually, they were much worse when I got this out of the package, and I actually tried pushing them back into shape, and I pushed them about as far as I dared to without breaking them. So they're almost in alignment right now, but definitely not. You can see how I can push it over, but it immediately comes back. So maybe with some more pushing, I can get them to line up. We'll find out. One other thing I noticed is that because I had no power, I happened to have my scope on, so I took my scope and I started looking at the voltage to see if thing was powered. And on the scope, it measured 5 volts just fine. On the 3.3 volts, it was measuring nearly 4 volts. It was just short of 4 volts. And I looked at the scope, I thought, that can't be. What? So because the voltages are generated by the Arduino board, and it's the Arduino board, if I take this off and I measure the 3.3 volts, the Arduino board is putting out 3.3 volts. It's very nice. Well, plus or minus a millivolt. But the key to that was that the Arduino board has some 5-volt signals that it's feeding up here for the SPI interface. The SPI signals are 5 volts. And so the SPI signals are being converted from 5 volts back to 3.3 volts through these level shifting chips here. I'm not sure which one has the SPI signal on it right this second, but one of them does. And I couldn't understand, why would it jump up the voltage on the Arduino's 3.3 volts. So I just, as a curiosity, because I'm dismayed with the quality of these boards and the intermittence that I'm getting off of this one, I went back and I checked on the Amazon site where I actually purchased these. And according to the users, these get some pretty low ratings, like 1s. and that's because that's the lowest you can give it. And one of the gentlemen, one person, I think he was a fella, who responded to why he gave a 1 rating, said that one of these chips is the wrong one. And sure enough, they're wrong on both. And he said that, according to his description, that there's 2 versions of these level shifters, almost identical, but there's one in which it doesn't have diodes between the 5 and the 3.3 volts. And that one allows the 3.3 volt conversion to be done without causing the 3.3 volts to jump up. Because there's some kind of a feed-through mechanism inside the chip that there was a second kind of chip designed which eliminates that, and it was supposed to be placed where the SPI signals come in. I probably should give some better description of this chip issue that I raised. I have a schematic that I found, which was put out by Circuits at Home. This schematic, I imagine, is fairly accurate to the original design, if not theirs. And so in the top left corner of this image, you can see that there's a chip shown called U6, and it's got a chip type called a HCT 125. And in the bottom right corner is another chip, U7, which is an AHC 125. So they're different. And there's another bit of information I found in this next image that was located on, it's on the electronics stackexchange.com as an answer to a question that was posted there. This was explaining the difference between the two chips I just mentioned, and it says that the HC version doesn't tolerate input voltages beyond the supply voltage, and it goes further into, it has clamping diodes on the input, the VCC and ground, so that if it's powered by 3.3 volts from the target and the input comes from a 5 volt signal, such as the signal we're supplying for the SPI control, that the signal gets pushed to the 3.3 supply, and it might push the 3.3 supply voltage up. Well, that's exactly what I'm saying, and that's exactly what the case is, because they have the wrong type of chip in place where it should be the AHC125. I'm going to do some side experimentation and see exactly what happens if I divorce this board from the SPI signals and then check the 3.3 volts and see if that makes us any better. And I'm also going to solder these unsoldered jumpers. As I say, my dexterity is not that great, so I'm hoping for the best. And I don't know, if I damage the board because of that, maybe I can get this one to work again, but it's beyond me. So you have a sense of my frustration. I apologize for that. But if I can't make better progress with this, I have yet an alternative plan for getting the JMRI software working on my model railroad with a laptop, because I just happen to have one that it was broken. And I mean, worse than the one that I broke. It's like, I'll explain that. There's a story involved in that one being broken. But I'm gonna, if I can't get these things working, I'm gonna short circuit this project and get the JMRI working on that PC, it's a laptop, and hopefully make progress where I can't seem to overcome the obstruction that this highlight dope is giving me. So let's move on, see what I can get done. So my plan right now is to solder the jumpers on this, what I'm calling the replacement highlight go USB host shield. And so I've got my soldering equipment out, I'll power that up, and my obligatory cup of coffee. By the way, the coffee cup is a cup that was presented to members of the L and KV, which is the Lehigh and Keystone Valley Railroad Model Club, several years ago. And I recently joined as an associate member, and was a cup I got from Bill, and just mention, Bill, thank you very much. It holds coffee. Well, the first thing I need to do is to, by the way, that says 400. I don't know if that's showing up on the video or not. This is the setting for the tip, and I got a very small tip on here. So I'm gonna first try to get some solder on the tip. So I got just to tin it up. And I want to make sure I can melt the solder. Okay, so I got a blob on there, and set that there for a moment, and get out my trusty applicator, toothpick, put a little bit whoops, I've got blobs all over. You can tell watching me do this that I don't solder that often. I used to, but it's been years since I did much. So I'll just set that aside for a moment. I got different kinds of different thicknesses of solder. Sorry about that. But let me see what I can do with this. Apply a little heat, and if I can get some solder on that. Darn, I'll go with a little thicker solder. All right. Oh, a little blob on there. So I've completed my soldering, and I hope this is showing up okay, but I got a little solder ball here, I got one here, and I've got one here. And hopefully the solder joints are good, but I will check, make sure that the voltages are correct and that there's continuity with my ohm meter. By the way, I had to jack the temperature up to 600 on the soldering station, and I finally was able to get the solder to flow. The lower temperature, 400, was not high enough for this solder. Okay, let's see how that turns out. What you see here is the experiment that I've set up for investigating the case where the 5-volt signal coming from the Arduino to the host shield is causing the 3.3 volt on the host shield to jump up from 3.3 to a voltage level closer to 4 volts, which, as discussed in the past, this particular chip right here, it's a 3421E USB converter chip, and that particular chip, as I've said, it's a 3.3 volt only operating voltage for that chip. So when the voltage gets pushed up, it's actually at an illegal state for this particular chip, which made this interfere with its ability to detect when something is attached. But anyway, the point of this experiment here is to actually look at the 3.3 volts, which I'm doing here. It's like I've got my scope over here. It's going to be monitoring the 3.3 volts, which I have on this breakout box here, which is that'll be the 3.3 volts there, and this is the ground return. And so, using all of these jumper wires, what I've done is essentially made the connection between the Arduino and the host shield as if it were plugged in. So I've also created, let's go over here for a moment, take a look at this. I've created this Arduino, whatever they call it now. It's a little application. But what it does essentially is it's going to toggle one of the lines. And one of the lines, if you recall that earlier there was a discussion previously about these SPI signals, and the only one of the SPI signals that really matters, it's going to the host shield from the Arduino, and it's the select signal. And obviously the in and the int signals they're 3.3 volt signals coming from the host shield. So the other one that might be an issue, this would be this, where I'm actually driving an output, or this, which is clocking it. But in this particular scenario, I only need one 5-volt signal going over to the host shield from the Arduino, so that's going to be this one, and that's what this Arduino app here does. That's going to toggle the 5 volts on and off based on an input from the serial interface. So let me try and run through that experiment, and what we're going to do then is just watch the voltage on the 3.3 when I toggle the select line high and see if it jumps up. Okay, so I'm going to actually run the experiment now. Currently you can see that there's roughly 3.3 volts coming from the Arduino. The Arduino is powered up, and the serial port is connected to this Arduino IDE's, the serial monitor that's showing down here. And when I enter the value of 1, the software that I wrote, as I just explained, will actually put a high level voltage out on the select pin, and we'll see how that affects the 3.3 volts that's going from the Arduino over to the host shield. So I'll do that now. Here's a 1. I'll enter that, and clearly that voltage is that's the voltage being applied to the 3.3 volt chip. That's the heartbeat of this host shield. So in the event that there's some, I better get that off of there too, by the way, so I'll turn that back off again. In the event that there's some functionality of the 3421E Maxim chip that's actually trying to detect something connected. If that's harming it, it might even be damaging the chip, because that voltage it clearly exceeds the maximum rated voltage for the 3.3 volt parts that are on this board. And it's clearly coming back from the board, because when we apply the high level voltage, as I've explained, the high level voltage on the select pin, 5 volts, is being converted through this chip right here to 3.3, but the supply voltage to this chip right here is 3.3 volts. So the 5 volt signal is somehow pushing the 3.3 volt supply to the chip through, apparently, as it's been explained, there's some clamping diodes in there that are causing that. So I'm not sure I can fix that, but I was wondering if I use this voltage divider here. When I say here, I mean here. I guess that there's some resistors here, and what it does is it creates a 3.3 volt output from a 5 volt input. So I'm going to just try to see if I were to take that select pin output, 5 volt output, and cut it back to 3.3 volts. Does that eliminate the issue that we're seeing with the voltage jumping up to over 4 volts? Okay, so I've got this set up now where I'm routing the select line, 5 volt select output, through this resistor divider network that I've got, and then back over to the select input on the host shield. And if anyone's wondering how I configured this, was I took 3 identical resistors. They're all 3.73 k ohm resistors, but it comes out to roughly 3.3 volts. And the next thing to do then is to enter a 1 over here so that I cause the select output to go high, which will be 5 volts over on the Arduino. So let's do that. All right. And it's still 3.3. So it has not impacted the 3.3 volt regulated DC output from the Arduino that's coming over here to the host shield. And the reason for that obviously is that we've cut the voltage back and we're not forcing voltage back into the 3.3 of the Arduino. So there's the experiment, and I think I've proven my case, but now the question is, can I continue to use this? Well, actually, this is the replacement host shield, but I'm wondering if I can continue to use the original host shield and be able to finish my software. So let's take a look at what I've accomplished so far. Well, my host shield is working. That is the original host shield. And I've been able to put together a presentation to introduce my efforts regarding the USB driver that I'm creating. So I'll present that briefly because this video has already become somewhat long. I think it's over 20 minutes, I think. So that's a bit too much. I will cover the host shield software that I'm creating in the next episode, and I'll try to be as complete as possible in that one. I'm hoping, keep my fingers crossed, that the host shield that I'm using will continue to work, and I'll be able to complete that software and I can move on to the next phase. One thing I'd like to interject right now, though, just as a forethought, was I showed that if I reduce the 5 volt to 3.3 volts using a voltage divider, that the host shield was a lot happier. I didn't get that pushback on the 3.3 volts from the 5 volts. And so in that line, I was thinking perhaps I could actually create some voltage reductions on the side and then feed the reduced signals somehow in a way that doesn't interfere with me packaging up the three different converters, because I'm going to have in the end, I'm going to have the Arduino, I'm going to have the Bluetooth, and then I'm going to have the USB all stacked. So I'm thinking about that. But anyway, let me continue with my presentation. What I'm showing on the left is my preliminary driver application that I intend to use for the NCE USB interface. At this point of the driver development, my goal is to show just two things. Show the library task method states when a connection is recognized by the host shield, and then secondly, to show the device configuration data. I've spent roughly 4 weeks doing a code walk of the host shield library. Reverse engineering it was the only way I had to figure out how to use this software. Because just like the host shield, the library comes without a manual. To make this task even more difficult, the author of the library placed a very low priority on creating code that's documented and easily comprehensible. The source essentially lacks any comments, and all of the methods, constants, and variables use cryptic naming conventions. I have successfully created this working application I'm showing here. About the code, as many of you already know, the Arduino microcontrollers are supplied with a tiny operating system that supports the application. It has a serial interface and then an application control. The setup, this method here, the setup method is called just once, and then once the setup completes, the controller then repeatedly calls the application's loop method. It's a simple but effective operating system. So what I'm showing now is the setup method in my driver routine. At a glance, you can see that basically all it does is it sets up the serial interface between the Arduino and the host computer that's monitoring that. The important part of it is actually the call to this INIT method, which is my software's init function, but in effect it calls the init method that's in the host shield library. And so that call actually initializes everything that the library needs in order to communicate with the 3421E USB chip. So the next thing that happens is that I go to the loop method, which I'm showing now, and the loop is just a bit up off the screen, but the first thing the loop does, and every time the loop passes through this execution thread, it calls the task method. And that's in my driver software that calls in turn to the library task. And what task is doing is it's basically asking the USB chip on the host shield over and over again, do you have anything? Have you got attached? So that's going to continue to work. And what will happen while it's waiting is that the library stays in a certain state each time it goes through. And the first state, of course, is waiting for an attachment. But this next method called do task state report is reporting those states. And when a device actually gets attached, then the states will actually go through a progression. They're state-wise controlled. It steps through the initialization. For instance, it sets up the correct baud rate that the device requires and a few other things in the USB host chip. And so the next thing that will happen, once it's connected and it's gone through all its states, calling this do state report will no longer do anything, but it'll return false, and it'll come down to the next step down here where it's going to call do device report. And what a device report is only going to happen one time, and it's going to go in and query the device for all of its configuration data. So there's the basic configuration for the device, and then there's the configuration for every one of its descriptors or for the interfaces that are involved within the device. I'll talk more about that next time. I don't want to bore you with a lot of that detail. But what I'm showing now is the actual data. And here at the top, you can see that the report was actually just showing the states, and here it was waiting for device, and then it goes through. When it goes to settle, that means it's detected a device, so it's just waiting for the interface to calm down. And then it's going to wait for a reset complete, because the first thing that a USB host does when it sees a device is it issues a reset command. And once that completes, which is just a timed event, it goes to start a frame, and then it goes to a reset, and then the state's running, goes into a running state. So once it's in the running state, of course, I just mentioned I drop out of the state checking, the state reports, and I go into the device report. And here it's showing that the device address is 1. That's how we communicate with it. And then there's a device descriptor that tells everything that's necessary to know about the device. And again, I'll go into the details in the next episode. This is just to give you an idea of what kind of things we saw. And as this thing begins to progress through, that's scrolling down to show you all of the different things that have been accumulated from this attached device. And the device attached right now, of course, is that PlayStation 4 controller, and it has quite a lot of things going on. Hopefully something within the video was actually of interest to you, and that you didn't have to sit here and listen to me chatter on and not gain anything by it. If anything was interesting to you, please leave a like and consider leaving a comment. I always like to read the comments, and I always respond. So if you have anything you'd like to add or criticize or explain how I might be able to improve my videos, I do appreciate that feedback. So don't be shy. Thank you for watching. I appreciate your time for sharing this with me.